Hello students, myself Henasha, Assistant Professor at LG Institutes of Engineering and Technology. So today we are going to discuss few more topics of sequence and series. So let us begin with its first topic, that is radius of convergence and interval of convergence. So if you are given a power series summation n is equals to 0 to infinity an x minus a whole raised to n, right? So here un is equals to an into x minus a whole raised to n. So in this type of power series, we know that we will always apply ratio or root test. So now let us apply ratio test, and for that let us find un plus 1. So un plus 1 is equals to an plus 1 into x minus a whole raised to n plus 1. So now on applying ratio test, right, we will get limit n tends to infinity mod un plus 1 upon un. Why we are taking mod? Because here x can be positive or a negative number, right? So we are taking mod un plus 1 upon un. So limit n tends to infinity. Put the value of mod un plus 1 and mod un. Now you can see that x minus a whole raised to n gets cancelled out. So what is remaining? Limit n tends to infinity an plus 1 upon an into x minus a. Now take this x minus a outside the limit. So mod x minus a into limit n tends to infinity mod an plus 1 upon an. Now we call this as n. So finally the answer of the limit is equals to x minus a into l. So now let us apply the conditions of ratio test. Okay. So for x minus a into l less than 1, that is for mod x minus a less than 1 upon l, the power series converges, and for mod x minus a into l greater than 1, that is for mod x minus a greater than 1 upon l, power series diverges, and for mod x minus a is equals to 1 upon l, the test phase. Hence we have to apply some other test. Okay. So here r is equals to 1 upon l is called radius of convergence. Okay. Now similarly we can prove the formula of radius of convergence using what? Root test. Okay. So now for a given power series, summation n is equals to 0 to infinity an x minus a whole raised to n. There are in all three possibilities, and they are: the series converges for all x when r is equals to infinite, that is whenever our radius of convergence is equals to infinite, our series converges for all x. Next, the series converges for x is equals to a when r is equals to 0, that is whenever radius of convergence is equals to 0, our series converges for x is equals to a. And lastly, if our r is any non-zero positive real number, then the series converges for mod x minus a less than r and diverges for mod x minus a greater than r. Okay, so from this we can say that the interval in which the series converges is called interval of convergence. So basically we have to apply ratio test or root test and find the radius of convergence, and from that we have to find interval of convergence using this formula mod x minus a less than r. Okay, so now let us solve an example. Here we have to find the radius of convergence and interval of convergence of the series summation n is equals to 0 to infinity minus 3 raised to n x raised to n upon square root n plus 1. So here you are given a power series where un is equals to minus 3 raised to n x raised to n upon square root n plus 1. So in this we will apply our ratio test. So firstly let us find un plus 1. So it will be equals to minus 3 raised to n plus 1. Just replace n by what? N plus 1. X raised to n plus 1 upon square root n plus 2. Okay. Now let us find limit n tends to infinity mod un plus 1 upon un. Because this is an alternating series, therefore we are taking mod. Now let us put the value of un plus 1. Put the value of un by taking its reciprocal. Now simplify this. So on simplifying, minus 3 raised to n will get cancelled out. So only minus 3 will remain. From x raised to n also will cancel out. So only x will remain. Now put this as it is, that is square root n plus 1 upon square root n plus 2. Now take this term outside the limit. So you will get 3 times mod x into limit n tends to infinity square root of n plus 1 upon n plus 2. Okay. Now let us take out n common from the numerator and denominator. So what you will get? N common 1 plus 1 upon n times 1 plus 2 upon n. This n gets cancelled out and finally what will remain? Square root 1 plus 1 upon 1 plus 2 upon n. Now we know limit n tends to infinity 1 upon n is equals to 0. So these two terms will go to 0. So finally the answer of the limit will be equal to 3 times mod x. Now let us apply the conditions of ratio test. So by ratio test the series converges for 3 into mod x less than 1 and diverges for 3 into mod x greater than 1. That is, we can say that our series converges for mod x less than 1 upon 3. That is, whenever x lies between minus 1 upon 3 to plus 1 upon 3, our series converges and it diverges for mod x greater than 1 upon 3. So from these two conditions, we can say that our radius of convergence r is equals to plus 1 upon 3. Now, before finding the interval of convergence, we will check for mod x is equals to 1 upon 3. That is for x is equal to plus or minus 1 upon 3. Right? So, firstly, let us begin by putting x is equals to minus 1 upon 3 in our un. So, un will be equals to minus 3 raised to n into minus 1 upon 3 raised to n upon square root n plus 1. So minus 3 raised to n will get cancelled out. So finally what will remain? 1 upon square root n plus 1. Now in order to check the convergence, we will apply limit comparison test, right? So take out root n common. So it will become 1 upon root n times square root of 1 plus 1 upon n. So assume our Vn as what? 1 upon root n, right? And find the limit n tends to infinity un upon dn. So 1 upon root n will get cancelled out. Only what will remain? 1 upon square root 1 plus 1 upon n. Now this limit will go to 0. So only answer will be 1, which is finite and non-zero. Now let us study our series Vn. That is equal to series 1 upon square root n, which is a p series with p is equals to 1 upon 2, which is less than 1. So our series is divergent, right? By which test? P series test. And therefore, by limit comparison test, our series un is also divergent. For which value of x? X is equals to minus 1 upon 3. Okay? Now let us check the convergence at x is equals to 1 upon 3. So put the value of x as 1 upon 3 in our un. So you will get un is equals to minus 3 raised to n into 1 upon 3 raised to n upon square root n plus 1. So this can be simplified as minus 1 raised to n upon square root n plus 1, which is an alternating series, right? So which test we have to apply? Leibniz test. So firstly check mod un minus mod un plus 1. Just put the value of mod un, which will be 1 upon square root n plus 1, minus put the value of mod un plus 1 by replacing n by n plus 1. So it will be 1 upon square root n plus 2. Now you can see that this is always greater than 0. And now find the limit n tends to infinity mod un. So put the value of mod un, that is 1 upon square root n plus 1. So again this limit goes to 0. Therefore, by Leibniz test, we can say that our given series is convergent for what value of x? X is equals to 1 upon 3. Thus, the series converges for minus 1 upon 3 less than x less or equals to plus 1 upon 3. Hence, our interval of convergence is minus 1 upon 3 to closed 1 upon 3. Okay. Now, let us study one more example. For the series summation n is equals to 1 to infinity minus 1 raised to n into x plus 2 raised to n upon n, we have to find the radius of convergence. And for what values of x will this series converge absolutely or conditionally, right? So firstly, let us write our un. So un is equals to minus 1 raised to n into x plus 2 whole raised to n upon n. So in this, we can apply our root test, right? So we will find limit n tends to infinity mod un raised to 1 upon n. Why we have taken mod again? Because this is again an alternating series, right? So limit n tends to infinity. Whenever you take 1 upon n, what will remain? Minus 1 into x plus 2 upon n raised to 1 upon n. Now we know as limit n tends to infinity, n raised to 1 upon n will go to 1. So finally what will remain? Mod x plus 2, right? Now let us apply the conditions of root test. So by root test, the series converges for mod x plus 2 less than 1. That is, whenever x lies between minus 3 and minus 1, the series converges, and the series diverges for mod x plus 2 greater than 1, right? So from this we can say that our radius of convergence r is equals to 1. Okay. Now let us check whenever mod x plus 2 is equals to 1. So mod x plus 2 is equals to plus or minus 1. So it can be simplified as x is equals to minus 3 or x is equals to minus 1. Firstly, let us put the value of x as minus 3. Okay. So on putting x as minus 3, your un will become minus 1 raised to n into minus 1 raised to n upon n, right? Now minus 1 raised to, this will become n plus n, that will be equals to minus 1 raised to 2n, which is an even number. So it can be written as 1 upon n. Okay. So now on applying which test? P series test. When p is equals to 1, we can say that the series is divergent for x is equals to minus 3. Okay. Now let us put the value of x as minus 1. So you will get your un as minus 1 raised to n upon n. So this is again an alternating series, right? So we have to apply which test? Leibniz test, right? So mod un will be equals to 1 upon n. So let us find mod un minus mod un plus 1. So which will be equals to 1 upon n minus 1 upon n plus 1. Simplify it by taking LCM. So you will get 1 upon n into n plus 1, which is greater than 0. Now find limit n tends to infinity mod un. But our mod un is 1 upon n. So put that value. So finally the answer of the limit will be equal to 0. So both the conditions of the Leibniz test are satisfied. Therefore we can say that our series is convergent for x is equal to minus 1, right? So finally the interval of convergence is minus 3 less than x less or equals to minus 1. Okay. Now our given series is absolutely convergent for minus 3 less than x less than minus 1 and conditionally convergent for x is equals to minus 1. Why we have written this? Because our summation un is what? Divergent at x is equals to minus 3. Hence it is not absolutely convergent at x is equals to minus 3. And whenever we are given our summation un, that is equal to summation minus 1 raised to n upon n at x is equals to minus 1, right? Now whenever we take mod un, it will be equals to what? 1 upon n, which is divergent by P series test. Hence, this is convergent. That is, our series un is convergent, but mod un is divergent at x is equal to minus 1. Therefore, we can say that it conditionally converges at x is equals to minus 1. Okay. Now, let us solve one more example. We have to find the interval of convergence of the series summation n is equals to 0 to infinity x raised to n upon n factorial. Firstly, let us write our un, that is equals to x raised to n upon n factorial. Looking at the factorial notation, we will obviously apply which test? Ratio test, right? So un plus 1 will be equals to x raised to n plus 1 upon n plus 1 factorial. Now let us find the limit. L is equals to limit n tends to infinity un plus 1 upon un. Put the value of un plus 1 and put the value of un by taking its reciprocal. Now we'll simplify this. So x raised to n will get cancelled out and n plus 1 factorial can be written as n plus 1 into n factorial, right? Now again this n factorial will get cancelled out and take mod x outside. So what will remain? Mod x times limit n tends to infinity 1 upon n plus 1. Now as n tends to infinity, this limit will go to 0. So our L is equals to what? 0. Now from the formula of radius of convergence, R is equals to what? 1 upon L. L is 0. So finally our radius of convergence is what? Infinity. So from this we can say that our given series is convergent for all the values of x, right? So in today's session we have studied radius of convergence and interval of convergence. We will find that using ratio test or root test. So I hope you have understood everything. Thank you for watching.